All right, so here we're going to do another series where we're testing for convergence or divergence, and we're going to use the integral test again. This one is trickier than the last one, just because the integration requires some techniques. But this is the series where we're going from n equals 1 to infinity of the natural log of n over n squared. So when you have the series given in summation notation like this, it's easy to find that function f of x. We just replace the n's with x's. We're going to define it to be natural log of x over x squared. That means that the improper integral we're looking at is the integral from 1 to infinity of the natural log of x over x squared dx. Now this is a slightly trickier integral to evaluate. I'll go ahead and write it in the limit notation first. The limit as t goes to infinity of the integral from 1 to t of the natural log of t over t squared dt. And then to evaluate this, we're going to start with a u substitution. I'm going to set u equal to the natural log. Oh, sorry, I don't want t's in here. I want x's in here. I don't want it to conflict with that t. Natural log of x. That would mean that du is equal to 1 over x dx, which is not exactly what I have here. I have a 1 over x squared. So if I just did u du, I would get natural log of x over x. To get that extra factor of 1 over x in there, I need to find out how to relate 1 over x to u. So notice here, if I take e to the power of both sides, e and that natural log are going to cancel to give me an x, which means if I take the reciprocal of both of these, giving me e to the negative u, that would be the same thing as 1 over x. So I can multiply u times du by e to the negative u, which would be equivalent to this. So that gives me the limit as t goes to infinity of, now my limits of integration have to change as well. So I plug a 1 in for x here, natural log of 1 is 0. I plug a t in and I just get the natural log of t. But now I have e to the negative u times u du. Okay, now this thing we can evaluate using integration by parts. And I believe we actually did evaluate this one using integration by parts all the way back in chapter 7, or at least one that's very close to it. But I'm going to let you fill in the gaps here since we have done this before. We want to take the limit as t goes to infinity of this integral. When you evaluate it using integration by parts, you're going to get negative u e to the negative u, and then you're going to get minus e to the negative u there, from 0 to the natural log of t. Again, I'm skipping the work showing that this is integration by parts, but this is among the easiest types of integration by parts problems you can do, so it's a good review for you to try that out. Now, if I plug a 0 in, natural log of t in, I'm going to get this, limit as t goes to infinity of negative t e to the, let's actually pull a negative all the way out. So have the negative right there. This will be the natural log of t. And then I'm going to get e to the negative natural log of t minus e to the negative natural log of t. When I plug a 0 in, this goes to 0, and this becomes minus 1 right there. But I'm subtracting that, so it's actually plus 1. Okay? Now, e to the negative natural log of t is the same thing as this. So off to the side, if I did e to the negative natural log of t, using an exponent or a logarithm property, that negative can be brought up here to give me e to the natural log of t to the power of negative 1. That's a logarithm property where you can take constants up into powers here. The e and the natural log then cancel each other out, giving me 1 over t, because that's what t to the negative 1 power is. So each of these guys becomes a 1 over t. And that means I'm going to get natural log of t over t minus 1 over t, or just natural log of t minus 1 all over t, like this. Okay? So now, let's see. So I also have that plus 1 there. And remember, what we need to do is take the limit as t goes to infinity of this. Now, this is an infinity over infinity indeterminate form, because both the numerator and denominator would go to infinity as t goes to infinity. That implies that I can use L'Hopital's rule. If I take the derivative of my numerator and denominator, I get 1 over t over 1. And this plus 1 I'm not doing anything with. It's just the constant. I'm going to leave it there. This will go to, this is the same thing as just 1 over t, which goes to 0 as t goes to infinity. So this equals 1 as t goes to infinity. Okay? Because this is finite, the improper integral came out to something finite. It converges, which means my series also converges. Okay? So that was a tougher one. The integration was a little bit trickier. Now let's look at a specific type of series that we can analyze using the integral test. So any series that takes this form, the series where n goes from 1 to infinity of 1 over n to the power of p. We call that a p series. These show up a lot, and it's good to be able to quickly check these for convergence or divergence. We've seen 2 of these so far. So we've looked at 1 over n to the second power and 1 over n to the 1/2 power, or in other words, 1 over the square root of n. Those are the first 2 examples we looked at. We've actually also looked at a p series of the form 1 over n to the 4th power in the previous video. So those things are good candidates for the integral test. Notice, first of all, when p was equal to 2, our series converged. That was the very first example that we looked at in this section. When p was equal to 1/2, giving me a square root of n down there, this series diverged. And let's look at some other values. What happens if p is equal to 0? Well, if p is equal to 0, n to the power of 0 is 1, and so this series just looks like 1 plus 1 plus 1 plus 1 infinitely. The sequence of terms there does not go to 0, so that would have to diverge. That's from our divergence test. If p is less than 0, then I can think of p, it would be a negative number here. So if you think of that as n to some negative number in the denominator, I can bring it into the numerator and make that exponent positive, which means that the terms of that series are going to get bigger and bigger and bigger. The limit would not go to 0. In fact, it would diverge to infinity. So in that case, we also have a divergent series. So we verified that if p is 0 or less than 0, our series diverges. Now let's assume that p is positive. That's the only case we haven't looked at. Then this function, 1 over x to the power of p, is definitely continuous, it's positive, and it's decreasing. We've already seen examples of that on that interval 1 to infinity. So we can apply the integral test to that. Again, we're looking at this integral, the integral from 1 to infinity of 1 over x to the p dx, convert that into this limit. And then notice if you follow the steps here, we end up with an expression like this, 1 over 1 minus p times the limit as t goes to infinity of t to the 1 minus p power minus 1. So really, it's this term right here, this t to the 1 minus p power, that's going to determine whether this limit goes to infinity or something finite. If p is greater than 1, then we're doing 1 minus something that's greater than 1, which would be a negative number. And t to a negative number, if we take t to infinity, that would go to 0. So in that case, the limit is going to exist, which means this converges. If p is less than 1, so because we're assuming p is positive, that means it would be between 0 and 1. Then we have a positive exponent here, because 1 minus something that's between 0 and 1 would be positive. That limit will go to infinity. So if p is between 0 and 1, we also have divergence, but if p is greater than 1, that's the only time that we're seeing this series converge by the integral test. And so we call that the p-series test. This series, which we call a p-series, 1 over n to the p, is convergent anytime p is greater than 1, and divergent anytime p is less than or equal to 1. So let's use that p-series test in an example, a couple of examples. So we've looked at this guy already. We've shown that this series, actually, have we? I think I am. No, I'm sorry, we haven't looked at that one yet. I was thinking of where it showed up here. This series, 1 over n to the 4th, converges because it's a p-series with p equals 4. That's the exponent on that n right there. And that's greater than 1, so by the p-series test, that series converges. Okay? What about this one? Here's a sum from n equals 1 to infinity of 1 over the 5th root of n cubed. This we can put in the form of a p-series by rewriting it as 1 over n to the 3/5 power. That's the same thing. And in this case, this is a p-series with p equals 3/5, but that is less than 1. And by the p-series test, this series diverges. Okay, so these are among the easiest series to test for convergence or divergence. You just look at what value of p you have, determine whether it's greater than 1 or less than or equal to 1, and then you get a conclusion from that. All right, the last thing that we want to do is estimate sums of series using this integral test. So for this, let's assume that we're looking at a series of this form, n equals 1 to infinity of a n. And let's suppose that it's convergent and its sum is some number s, some finite value s. What we can do in a series like this is we can treat each partial sum, Sn, as an approximation to the sum of the entire series. And it makes sense that in most cases, the larger n gets, the better an approximation we get. But we want to kind of analyze that a little bit more, quantify how good of an approximation we get with different partial sums. So to that end, let's define this thing here as a remainder, Rn, and we define it to equal S, the actual sum of the series, minus Sn, the nth partial sum. Now remember, the nth partial sum adds up the terms from A1 all the way up through An. So if we're taking the actual sum of the series and subtracting that partial sum from it, then that's going to leave us with just all of the remaining terms in that series, An plus 1, An plus 2, on to infinity out here. If we are dealing with the type of series that we can model with a real valued function that satisfies the criteria of the integral test, which means it's continuous, positive, and decreasing on the interval from 1 to infinity. And if f of 1 is equal to the first term of our series, if f of 2 is equal to the second term, and so on, then what we can do is use sort of our reasoning behind the integral test at the beginning of this section to find a way of bounding this remainder term. So here's the way we're going to do that. Remember, this remainder term gives us the sum of all of the terms of our series after the nth one. So starting with n plus 1. So if I look at the function y equals f of x and graph it, and then take the interval that goes from n to infinity, break it up into subintervals of width 1, and construct these rectangles with right endpoints, then as we saw before, the area of each one of these rectangles is going to represent one of the terms of this series, so that the combined area of those rectangles is the sum of that series. Here we're just looking at the sum of these values. This ends up being an plus 1, an plus 2, and so on and so forth. If I use left endpoints instead of right endpoints, and if instead I look at this interval from n plus 1 to infinity, the left endpoint of this interval is going to agree with the the left endpoint of this interval is the same as the right endpoint of this interval. So the height of this rectangle will be the same as the height of the first rectangle in the previous picture that we just looked at. So again, in this case, I get an plus 1 plus an plus 2 plus all the way through. So the sum of these rectangles, just like the sum of these rectangles, gives me that remainder term. Now, in one case, I have an overestimate, whereas in the other case, I have an underestimate for the area under the curve there. So if that improper integral of f of x from n to infinity or from n plus 1 to infinity exists, then the area that it represents has to be greater than or equal to this, but less than or equal to this, because of the overestimate and underestimate that we're seeing. So this is where we get something called the remainder estimate for the integral test. And it says this: if you have f of k equals ak, where f is a continuous positive decreasing function, remember those are the conditions of the integral test, anytime x is greater than or equal to n, and if your series of these terms is convergent, and if we define the remainder term the way we did previously, s minus sn, then that remainder term is going to be greater than or equal to this improper integral, but less than or equal to this improper integral. So it's somewhere between those values. And the reason that works is because of the overestimate and the underestimate for those areas that we just looked at. Okay, now these two improper integrals are almost the same, but this one starts at n plus 1, whereas this one starts at n. So I want to use this fact in an example in a moment. But if we also use the fact that the sum of our series is equal to the nth partial sum plus its remainder for each n, then we can write this as sort of a corollary to this. Notice I can write Rn equal to s minus Sn. So I can replace this with s minus Sn and then add Sn to all three parts here to get an s here. So that s is somewhere between Sn plus this improper integral and Sn plus this other improper integral right here. Okay, so now what I want to do to wrap this section up, I want to consider this p-series, which we've already shown converges in a previous example, and find a value for n for which Sn is within 0.00001 of the actual value of the sum. So basically what we're doing is we're selecting an error tolerance. We're saying that we want our nth partial sum to be good enough to approximate the true value of this thing within this tiny little margin of error, but I need to know how many terms of that series I should add up to get that good of an approximation. So what we're going to do is use this part of the remainder estimate. I want my remainder to be less than or equal to this value, but if I can get this improper integral to be less than or equal to that value, then it will guarantee that my remainder is as small as we want it to be. So what I'm going to do is look at the integral from n to infinity of 1 over x to the fourth. Okay, 1 over x to the fourth. Now that's the same thing as the limit as t goes to infinity of the integral from n to t of x to the negative fourth power dx. That's an easy integral to evaluate. So we get negative 1/3 x to the negative third power, again from n to t. Let's bring that negative 1/3 out. Limit as t goes to infinity. When I plug a t into here, t to the negative third power is the same thing as 1 over t cubed minus 1 over n cubed. That's what I'm going to end up with. Now, as t goes to infinity, this 1 over t cubed is going to go to 0. And so I'm left with negative 1/3 times negative 1 over n cubed, which is 1 over 3n cubed. This thing we would like to be less than this. Or less than or equal to, so 0.00001. This is the same thing as 1 over 100,000. Yep. So to do that, I can cross multiply both sides. This is going to imply that 100,000 is less than or equal to 3n cubed. I can divide that by 3 and then take a third root of that to say that n has to be greater than or equal to the cube root of 100,000 over 3. That's going to go into a calculator. If I plug that into a calculator, I'm going to get approximately 32.18. Now, n needs to be greater than or equal to that. Whoops, there we are. But n also has to be a positive integer. So I need to take the next largest positive integer. Let's set n equal to 33. Okay, so if I look at the problem, it says find a value of n for which Sn is within 1/100,000th of the sum, and this is that value. We could go and find what that sum is. You would be adding the first 33 terms of this series. You would want to use like a series calculator for that. That's a lot to do by hand, or even entering those values one by one into a calculator. There's series calculators out there that you can use that do that much more quickly. But that's it for 11.3.